Uh, and good morning to all of you. My introduction is over. Right now, I would like to say a few words before starting my presentation. Fundamentally, I am chemist, but right now, I have never done chemistry. And I mostly deal with material science and engineering. Most of the research areas are related with the processing of materials and their applications. And I am dealing with only one problem of material science, that is the role of solvents. Chemistry people use a lot of solvents. Some solvents are chlorinated, some solvents are hydrocarbon-based solvents, some are hydroxy solvents, some oxygenated solvents. And solvents have unlimited varieties. And these solvents play a very typical role, particularly related to health issues in our society. What we chemistry people do after processing, we discard the solvents in the environment, or either we do pollution through evolving certain kind of the gases to the environment that has created big problem across the world. Next problem is the disposal of the plastics. Plastics are disposed to environment and they have no way to biodegrade, or maybe they are recalcitrant. That is why their disposal is a big problem. So, since working in the area of material science for the last 30 years, I have concentrated my whole research in the area of how to remove the solvents from industry. And I got the success to remove the solvent from industry in several processes, more than 6 types of processes I will share, wherein I have successfully removed the solvents. Not only removing the solvent, but also I reduce the cost of production, because solvents are very costly. And when we manage the solvents, we have to procure them in a very large space. So how we can reduce the size of the industry just by utilizing less and less quantity of the solvents. And moreover, when we prepare the plastic materials, or there is a kind of agro-waste material, we cannot discard it. So how we can biodegrade the kind of materials, or how we can prepare, or how we can fabricate the kind of materials which are biodegradable. So I find a very miraculous kind of solvent, a very single solvent that can be tuned to the properties of the different kind of solvents. For example, if you want to process polyamide, you will be in need of dimethyl sulfoxide or dimethyl formamide because they are soluble in amide type of solvents. You want to prepare polyamides. Professor Nasimuddin was saying that polyamides are used along with graphene to form the nanocomposite material that is used for antennas. So graphene is also insoluble in all kind of solvents, and polyamides are mostly insoluble in all kind of solvents. But we can dissolve polyamide and graphene in certain kind of solvents that we have devised. And the solvent is very easy. Just I am making this way and questioning what is that. The solvent is very interesting, that is available in our environment. This is carbon dioxide. You believe carbon dioxide is available in our environment. We can use this carbon dioxide as a very potential solvent for variety of the industrial processes. I have developed the kind of technology wherein we have used carbon dioxide as a solvent to prepare the polymer materials. Not only polymer materials, but also other kind of hybrid type of materials, metal carbonyls, metal nanoparticles, and other kind of things. So I will share this very interesting event. First of all, this is my department, and my university is G.B. Pant University of Agriculture and Technology in Uttarakhand region of India. This university is having QS ranking 209, and the university is actually spread over 1,600 acres, and that is a very largest campus across the Asia. The university is having 7 colleges, and there are more than 500 type of departments. My department is the Department of Chemistry, where we deal with master's and PhD programs in chemistry, agricultural chemicals. We have intake of 500 students per semester. We have sufficient funding from different kind of funding agencies, ICAR, AICT, UGC, Department of Biotechnology, DRDO, Uttarakhand Council of Science and Technology, and many more. my focus of research is actually, most of the research is actually funded by DRDO, which is a Defense Development Organization. That is, those who are from India, they are knowing well that this is the organization that deals with defense systems. We do research in the area of defense. So my most collaborations are with DRDO people. That is why I have some binding that I cannot disclose most of my research, particularly what is here, but I will do the outline. We always believe in collaboration, and most of the area of research is related with material science, but my other colleagues do research in the area of pesticide residue analysis, natural products, and agrochemicals. We prefer collaborations. My research group is engaged in the area of polymer materials, particularly synthesis and processing of polymer nanocomposites, organic semiconductor processing, sensors and detection systems, photodegradation of recalcitrant materials like pesticides, polymers, organic matters, supercapacitors, particularly in the area of energy storage. We design certain kind of electrode materials for energy storage applications, as well as we deal with waste to wealth. We manage how to transform waste into wealthful products for commercialization. Antimicrobial nanomaterials, we have the kind of, the area wherein we transform plastic materials into antimicrobial films. Nanotoxicology, herein we investigate the effect of nanomaterials on crop systems and animal systems, on animal and crop health. And then bioenergy, bioethanol and transstabilization process, wherein we use how to transform biomass into bioenergy, particularly bioethanol and syngas. In condensed matter physics, we disperse ferrite materials into polymers. You have attended that lecture wherein we use ferrites for antenna preparation, for semiconductor preparation. So we prepare ferrite materials and we disperse ferrite materials into polymer matrix by means of carbon dioxide technology. Corrosion and construction materials, where we use civil engineering kind of the work. We prepare bricks, we prepare high performance, ceramic structures for civil engineering, for construction materials and polymer biodegradation. Our research group is well off with most of the modern analytical techniques. See, this is our network of collaboration. We have a very dense collaborators, as we can see through Erenis. My profile is available on Scholarpedia. You can go through. This is the region of Uttarakhand, very, very small region. And this state was created in India in 2003. Right now, I have 4 collaborations with British University of Egypt, Taiwan, Tribhuvan University, Nepal, and then UNC University of Taiwan, and the University of Washington, US. See, we cannot live without these materials, polymers, polymer products. They are the drivers of our society. Herein we can see that most of the materials are either plastics or resins or biomaterials or biocomposites or polymer composites or ceramics. All these materials are very important for our cozy and comfortable life. So we cannot live without this, but we want to discard all these materials. This is the problem, that we want these kind of materials and we don't want at certain time. Why? Because these materials are recalcitrant. So, the polymer consumption per capita is very high in North America, followed by West Europe and then East Europe and then China. India is somewhat lower. South Asia and Latin America is a bit high. And global production forecast of, the plastic products, it is expected that 30% will be rise in 2050 compared to 2025. Day by day, the dependency of the people, dependency of the society is growing on plastic products and polymer systems. However, these materials are very much recalcitrant. We cannot dispose of to environment. Why? Because these materials are very, problematic. So there is a need of the technology that should be environmentally benign. Okay, we can reduce the waste, we can reuse it or we can recycle it, and moreover, there should be some economic growth. These are the primary role of the solvents in polymer processing. Viscosity modification, particularly in spinning of fibers, application in coatings, dissolution and dispersion. This is a very important aspect of polymer chemistry or polymer science, wherein fillers are dispersed into the polymer matrix with the aid of the solvents. In the same way, polymer synthesis and blend preparations, and in recycling, those people who are well versed in material science, I mean in polymer science and technology, they are well known that once we prepare a blend, and if the blend is made between two thermoplastic, then it is very easily to blend. Why? Because a common solvent is sufficient to blend these kind of materials. But if material, one component is thermoplastic and one component is thermosetting, then it becomes very much difficult to blend it because the solvent is not the common. Some solvents are compatible to thermoplastic materials and some solvents are compatible to thermosetting materials. So ultimately, we cannot combine these kind of materials through, through traditional way of the solvents. In the same way, recycling is a very active area wherein too much organic solvents are used. In the same way, additive and filler integration, when polymer modification, polymer nano composite, polymer nano hybrids, these materials. For example, if you want to dissolve ferrocene, or if you want to dissolve, for example, graphene into polyamides or polyamides, it is very difficult to disperse through organic solvent. Why? Because graphene is insoluble in most of the organic solvents, as well as polyamides are not much soluble. So that is why the organic solvents or traditional solvents are not much effective for polymer industry. In the same way, specific fabrication methods, wherein cast preparation, film formation, membrane formation, organic electronics. In organic electronics, for example, semiconductor preparation, first of all, you want to dope a p-type material into n-type or whatever it is, something is polymer, for example, polypyrrole. If you want to dope, for example, metal ions or metal nanoparticles or ferrite nanoparticles into polypyrrole, definitely it is a very difficult task because polypyrrole is insoluble in most of the organic solvents. In the same way, ferrite is also insoluble in most of the organic solvents. So it is very difficult to compatibilize these kind of components through traditional solvent-based chemistry. See here, there are. See here, these are some sort of the solvents we have tried to categorize it. Some solvents are recommended; they are not toxic in nature, whereas some solvents are very difficult; they are highly toxic in nature. So most of the hydroxy solvents, for example, isopropyl alcohol or esters or phenols, they are usually recommended in polymer industry because they are less persisting in the environment or they are slightly more biodegradable. In the same way, some aromatic solvents, some benzene containing ring solvents or some polyether type of solvents are toxic in nature, or in between prohibiting and recommended, there are a few categories, and highly hazardous ones are that of the chlorinated solvent. Whole of the laboratories of the polymer industry, particularly those dealing with polymer chemistry, if you visit their lab will be full of bottles, so many bottles. Even when I was a student in Lucknow University, UP, India, my supervisor's laboratory was packed with so many bottles. When I joined the lab, I think that how it is just like it came in shop. So this is very difficult. In my opinion, what I have done in my research life, I have removed all the bottles from my lab. If you visit my lab, there you will find no bottle. Only you will be having a one carbon dioxide cylinder and one pilot reactor that I have procured. Now I have the way to design it also. If anybody will be interested, I can help you to design the kind of the pilot, benchtop pilot projector, benchtop pilot, reactor type of system. So this is what, a very typical and very horrifying thing that we are using so much kind of solvent. Even I have used pyridine many times. And when I use pyridine to dissolve the polyamides, what happened after 6 months, I have read somewhere that pyridine is anti-fertile. If anybody is working in the area of pyridine or is dealing with pyridine, after 1 year, he will become unfertile. This is very difficult. Yeah, sterile. So what is the problem with these solvents? Because these solvents are very toxic in nature and we are dealing with these kind of solvents. Even in small kids, just the age of 20 to 25 years of human being in the lab, I have seen that these people are using the kind of the solvents, and these solvents are very much disastrous to their health. So that is why it is a very important way to discard all these kind of organic pollutants from our laboratory environment and to replace them with the eco-friendly or with a human-friendly or environmentally benign system. So that is why I have developed this. See, garbage is a very big problem. Everybody knows that plastic is a recalcitrant. Plastic cannot be xenobiotic. It cannot be degraded. We have successfully degraded 1 dozen kind of the plastics, and we have a lot of the patents I will show. In the same way, for global recycling, US dollars of 68.12 million was actually 2022 related to the purchase and procurement of the organic solvents, and it is expected that this purchase of the organic solvent will be raised to US dollar 965.1 millions in 2030. So much problematic. We are expending so much amount of money on these solvents, and ultimately solvents are not the proper solution for the industry. Why? Because procurement is very important factor. It is problematic, as well as their cost is very much problematic. Their hazardous nature is very problematic. Many times industries, you observe that there is a fire. Industries catch fire because of the flammable solvents. Moreover, the problem with health issue is very important. Infertility, skin, liver, kidneys, CNS system disorders, and cancer, right? So this is what the problem related with solvents. Here is our technology that we have developed. Technology is very simple. You have carbon dioxide here in our environment. I think some 25 to 30% CO2 raised to our environment within 24 hours as an average. So what we do, we explore, we extract carbon dioxide from the environment, and then we pressurize this carbon dioxide at 31.5 degrees Celsius, which is a human-friendly temperature, at 72 atmosphere. That comes around 1100 psi. And what happens at this stage, carbon dioxide becomes liquid. And when liquid carbon dioxide is produced, see here, this is the phase change, where in a gas-liquid equilibrium, this is, here is a equilibrium at critical point. But when we increase the temperature and pressure, what happens? This phase change becomes unified into a single phase. That single phase is a supercritical phase. By the way, people have tried across the world as a ethanol, isopropanol, hexane, propane, methane, sulfur hexafluoride, air, argon, all kind of things as a source of producing the supercritical fluid. But carbon dioxide is a very economic supercritical fluid, followed by water. Water can also be used as supercritical fluid. So this is a very economic fluid because carbon dioxide is easily available in our environment. We can simply procure carbon dioxide from environment. We can charge into the reactor. I will show you how we can do it. See here, this is our reactor system. We are using this kind of the reactor system over last 25 years or more than, I think 25 years are. So here there is a vessel. We charge carbon dioxide from here, and this goes into the vessel. We chill the vessel to, for example, to 5 degree or below 5 degrees Celsius. So below 5 degrees Celsius, what happens when carbon dioxide is introduced into the vessel? Carbon dioxide is transformed into dry ice. And when it is transformed into dry ice, finally, if we heat up the dry ice into confined volume, it expands and then finally liquidates into liquid carbon dioxide. And when it is in liquid state, for example, you have maintained the temperature of 70 degrees Celsius and a pressure of 1200 psi. It simply behaves as a hexane. And when you increase the temperature, for example, to 90 degrees Celsius and pressure to 4000 psi, it simply behaves as a chloroform. Its entire solubility properties actually change. So a single carbon dioxide can be used as a hexane as well as chloroform. Even if you want to tune up the environment of carbon dioxide into ethanol, for example, any alcohol, let us suppose that some compound X is soluble in alcohol and you want to dissolve in the carbon dioxide. It is very easy to charge the reactor with that compound, charge the reactor with carbon dioxide, and maintain the temperature and pressure that is suitable or that is compatible to preparation of the alcohols, and that is around 2350 psi and 75-78 degrees Celsius. That temperature and pressure combines with the property of ethanol, ethyl alcohol. So in this way, there is only one solvent and millions of the organic reactions you can do by utilizing a single carbon dioxide system. See, since this presentation is solely devoted to materials, that is why I have confined my slides to polymers. What happens? Carbon dioxide is a molecule. This is having a random movement, and when we pressurize carbon dioxide, this shows Cauchy phase transition. And what happens? at a liquid state of carbon dioxide, we can execute the process of copolymerization, wherein we charge the reactor with CO2 with monomers, and then finally we add some sort of polymerization initiator, for example, benzoyl peroxide or azobisulfonitrile or maybe others, and then we maintain the temperature and pressure. Finally, we co-polymerize, we polymerize the monomer into the products. In the same way, carbon dioxide can be used to infuse ferrites and carbon nanotube into polymer matrix, or even those fillers which are actually magnetically stacked fillers or fillers with van der Waals stacking. For example, graphites, they are van der Waals stacking, and ferrites, they are magnetically stacked fillers. So simply carbon dioxide is actually it diffuse into the graphite matrix, it diffuse into the ferrite matrix, and finally it mixed with the polymers. And then when we depressurize the system to isolate the product, the whole product is isotropically distributed. That is, ferrite or graphene or carbon nanotubes or carbon nanomaterials are uniformly distributed into the polymer matrix. In the same way, we can also prepare foams. We can also prepare the kind of the lightweight materials by simply tuning the glass transition temperature of carbon dioxide. We can prepare bioethanol. My students have prepared bioethanol with 89 to 90% recovery from bagasse, which is a biomass, and which is a plenty amount of biomass having no applications. Only one kind of application is the paper, pulp and paper production. So how we have done this? We have shown you that carbon dioxide in the form of the liquid state was treated with the bagasse in presence of lipases, wherein fermentation process takes place, an entire biomass is transformed into bioethanol with a very good high yield. We have the patent. These are some of the technology. Though I have right now, I have almost 16 patents granted, and 3 patents are in the technology transfer process. This is our first kind of technology that is transferred to Biotech Consortium India Limited, India, and this technology is actually under transfer to Jain Biologicals India, along with one more partner is there. So Johnson & Johnson, one more partner, Johnson & Johnson. So herein we have prepared antibacterial plastic. How we have prepared antibacterial plastic? This is very simple. We have 2 kind of ways to prepare antibacterial plastic. First way is to load the monomer and antibacterial filler, which may be a zinc oxide nanoparticle, or maybe clay nanoparticle, or maybe silver oxide nanoparticle, or any kind of the nanoparticle which is showing antibacterial activity. We have tested the antibacterial activity. So many bacteria, Acinetobacter, Enterobacter, E. coli, Mycobacterium, so many strains we have, dozens of strains we have investigated for antibacterial action. So what happens there? We charge the reactor system with a monomer, with a catalyst and some sort of antibacterial filler, and we polymerize it. What happens? The filler, antibacterial filler, distribute into the polymer matrix, making the whole plastic to be antibacterial. For example, let us suppose that we want to prepare, or we want to fabricate a water bottle. We want that water bottle should be antibacterial. Water is there, and water should not be contaminated with bacteria. So if we prepare the whole bottle with that kind of antibacterial composite, this water bottle will be free from bacteria. Right now, this material is actually under technology transfer with the interest to prepare the battery plates, and these battery plates should be antibacterial at some sort and antiviral at another sort. In the COVID period, what was there? That bacteria was actually virus was there, and some sort of the problem was there when they grow the virus. Ultimately, bacteria also grown. At the same time, the antiviral activity of the material was compromised. So what happens there? In order to resolve the kind of the problem, we have developed the polymer products that are antibacterial as well as antiviral. So this is our patent. This is the material related to missile development program. Actually, I have been associated with Advanced System Laboratory, which is the laboratory of DRDO in India. This laboratory has been the laboratory of our missile man, Professor Kalam. So I have been associated with him through this laboratory, and there was a project of Agni missile. Right now, this missile is very active, application, and it is one of the important assets of India. So herein we have developed the kind of the kind of the material that is actually of high heat resistant and high mechanical resistance, and simultaneously having wear resistance. This is the nose cone of the missile. We were actually in the team of the designing this nose cone of the missile. So what we have done, clay is insoluble in resin. Clay doesn't dissolve in the resin. But here in what we have done, we have charged the clay. Clay is a phyllosilicate. Montmorillonite clay, which is a phyllosilicate, which is a layered silicate of the two aluminosilicate layers. What happens if you want to dissolve the clay, which is an inorganic material? It is perfectly insoluble in organic polymers, in organic materials, for example, resins or in organic solvents. But herein we successfully dissolved clay into resin. How we have done? We have charged the reactor with clay and resin and charged carbon dioxide. What happened? Due to surface tension, carbon dioxide was introduced in between the two layers of the clay, right, along with the resin. And once we have depressurized the system, the carbon dioxide was actually exploded, or it was expanded between the two layers, and the layers were bursted into the single nanostructure, one-dimensional nanostructure. So in this way, the clay, which was actually insoluble in the resin, we have introduced CO2 in between the interlayers of the clay. And what happens after expansion in between the layers? The layer was broken and the whole clay became in one-dimensional nanostructure. So later on, DRDO has utilized the application of these kind of materials as a dental filling, as well as in fabrication of the helmets for militaries. This is our next, very important task, very important project, whereas we have used stubble. Stubble in India, it is known as parali. We have used stubble, and there was actually a time when farmers of the India were too much worried, and I was just having my dinner in my house, and my wife asked me that why you are so proud, why you are so in question that you worried about this. What you want to do about this stubble? I said that just after finishing my dinner, I will work on this problem, and I have spent 2 nights continuously, 1 day and 2 nights to resolve the problem. Finally, I got the solution. I have transformed this, stubble into particle board. But the transformation of stubble into particle board was a very tough process. When we tried to transform this stubble into particle board, stubble was releasing the oil, bio oil. That bio oil was a very big problem. So I have extracted this bio oil from carbon dioxide technology, making stubble to be bio oil free, and then thereafter mixed with binder, and we just hot pressed, and now it is okay. Now it is the time. Now it is the time is going, but I would like to finish. So what is here? This is a very successful method. This is the production of bioethanol. What I have told you, we have transformed bagasse into bioethanol just through treating this with lipases in presence of carbon dioxide, where fermentation process takes place, and ultimately we got the good yield of bioethanol. This is the controlled drug delivery system and controlled pesticide delivery system, wherein we can transform the sterile land into fertile land, or even anti-cancer drugs. We can also prepare the target drug delivery systems. This is one of the major applications wherein we have blended silicone oil with epoxy resin, and this is a biodegradable, high strength biodegradable product that we have prepared. Sometimes polymers are biodegradable, but they are not mechanically viable. But there is a need of the material which should be mechanically stable, mechanically with high mechanical strength, as well as biodegradable. So this is the kind of material we have to. This is the semiconductor, wherein we have done copolymerization of polypyrrole and polythiophene liquid carbon dioxide. This material is having good class of conductivity. Here is the ferrite material. We have dispersed ferrite material into polymer matrix, what I have told you. This is the dispersion of graphene into polymer matrix. We have successfully dispersed graphene just like clay into polymer, because graphite is also a lamellar structure. We have accordingly dispersed graphite into graphene, just exploding into carbon dioxide, transforming into one-dimensional nanostructure. This is again the same kind of the task, wherein this is the biodegradation. We have transformed so many recalcitrant plastics into biodegradable products, and we have degraded polythene, polypropylene, and all kind of materials. This is very simple process where we have porogenized plastic with carbon dioxide in presence of some food, for example, some starch or some sort of carbohydrate. Since bacteria actually use these materials as a carbon source and has grown to log phase, finally at the log phase we have found that the materials were biodegraded. So even people think that polythene cannot be degraded, but we have 3 patents wherein we established the technology of biodegradation of polythene. Not only biodegradation, but we have also transformed the polythene into useful products, for example, wax and oils, through the process of biodegradation. This is my one last meeting with Professor Konstantin Novoselov. He is the man behind the discovery of the graphene. He is a Nobel laureate. And Professor Francis Arnold, he is the mechanical engineer, but he got the Nobel Prize in the area of the discovery of enzyme that has actually break the myth, religious myth, that man has came from Quran or Bible. This has came from a routine process. That routine process is reptilians to man, and then man is here. So this is what we thank you for your kind attention, and thank you for Mathews for giving me this nice opportunity to show my work here to this nice gentry who can understand the science well. And I would be very much interested if you are having some offer of collaboration, particularly in questions.